Here we gonna focus, so looking at the title, we're gonna focus mostly on the actual map and less on the traverse. If you are interested more in a specific traverse study, without a specific mission in mind, that is, but a general traverse study, I refer you to the video recording of the LPC special session of my talk. That's still gonna be online for another 2 weeks. Next slide, please. So we produced a map at a scale of print scale of 1 to 27,000, a mapping scale of 1 to 8,000. We did this for the original outlines of areas 1 and 4, and I believe in the program there was a typo calling it 1 and 3. Anywho, this is 1 and 4 as it was originally laid out. The outlines have changed a little bit. This was the specific extent was also determined by Mike Barker's DTMs that were available at that time, roughly 2 years ago. So we did this in an effort to not just get an inventory of the geomorphology of the area, but also to assess the best way how to connect certain dots of scientific interest, which then led to the traverse eventually. So here we want to delve more into how we arrived at this product and so what the future might look like. Next slide, please. So mapping the moon at such a scale and then around the poles is a specific challenge. Next slide, please. The main problem is, of course, that at this scale, you don't really see actual geologic units. You see mostly textures and regolith. You don't see geologic contexts in the classical sense. But the scale we're looking at is required to make the map usable as a field map, ideally, in the future. Furthermore, most compositional data that we usually employ to inform any classical geologic mapping on the moon is not applicable here, as M-Cube, Kaguya, Clementine, they're just too coarse to use as a mapping unit, certainly as a base map, but even to inform the characterization of our units. They're just too coarse. Furthermore, the elimination conditions are, as you can see in the very fresh NAC mosaic on the right, are very challenging, even with an ideal data product. This makes judging albedo very tricky. So usually we employ albedo to differentiate surface units, at least to a certain degree. But here we deemed that this is a slippery slope that we don't want to go down, as the lighting conditions often trick you into false albedo readings. And only in very few cases can you be certain that you actually see albedo variation of the surface. Now, so far for the units, the line and point features that should be in such a map, as I will also elaborate more in the following slides. And as you can immediately recognize on the NAC image here, for example, or the crater rims to block the slum scarps. Now, other things that we considered, and this is more elaborated more on in our full-scale publication from last year, and it was also touched base on in terms of the Shackleton injector by Brett in the previous talk, and mostly what you talked about, the Tycho arrays, of course, something that we considered, and no specific signatures in a geomorphic sense were identified by either features. We also looked at wet color data. So the entire area you see here in this image shows if it has a signature by Tycho and Shackleton, a homogeneous one that doesn't vary based on the data set that we can assess. Next slide, please. The closest analog to this area on a connecting ridge or any South Pole area would be the Apollo 16 landing site. So the Card Highlands are, well, the only highland site we ever visited, the only true highland site. And the main goal, or let's say a minimum goal, science definition goal of this mapping was to achieve the usability that the pre-landing maps had of the Apollo days. Here you see the Apollo 16 site. There are certain distinct differences in terms of the geomorphic inventory, of course. Also, at this point, a quick shout out that these maps are being redone. These areas are being remapped to reassess their the cratering inventory for the cratering chronology that's based on these areas. Suffice to say that the mapping refined a great deal, but it didn't revolutionize the general units, of course. So even the modern remapping products, which are not published yet, that's why I'm not showing them, don't look drastically different, yet refined. Next slide. The first order similarities that we can find and the differences between those two areas is of course that there's no such thing as a South Ray or North Ray crater or a Baby Ray crater in the area. There's no distinct crater ejecta units that we could map. Also, there's a general lack of very dense secondary clusters associated with such young craters, therefore. Also, the highland portions here, as the massif, the higher standing portions, the connecting ridge itself, therefore, lacks the lineaments that we see in Stone Mountain and also the Smoky Mountain area further to the north of the Apollo 16 landing site. Just a general comparison of the inventory here. The distinct contacts that we can see between the higher standing areas and the Highland Plains areas, the actual unit that Apollo 16 landed on, such a distinction is not just not there on a connecting ridge site. Um, the plains and the massifs, there's no plains unit to begin with. It's all hummocky surface. The connecting ridge, of course, if you know, shows no distinct context to the surroundings. Everything is covered by regolith that transitions from one texture into another. Nevertheless, we do see some smooth crater floors. That is the blue unit on the right-hand map. These smooth crater floor units cover some of the older and, let's say, mid-sized craters around Shackleton. And this is pending a further investigation, how far away from Shackleton they occur, what's the exact geographic association with Shackleton crater, and therefore also potential genetic association with Shackleton crater. And blocky knobs, that's something I'm going to show you in a bit, has been discovered by previous authors, for example, by Goransky et al. We don't see them in the Apollo 16 landing site, for example. So there are boulder fields in the Apollo 16 landing site, plenty of them, but these distinct blocky knobs are something special. Next slide, please. Now the crater rims to this, that's pretty straightforward, I'd say, for any lunar map at this scale. We categorize them according to degradation state. There's the only thing I want to point out to here is there's a category 3A and 3B. Those are distinct crater chains that we identified. The crater class 3B, for example, is the crater chain that goes along the connecting ridge. So we interpreted these as Korean crater chains that pertain to a formation, a secondary crater chain. There's another one off the extent of this mapping, of this cropped image of the map here, that is parallel to the crater ray, and therefore there's a tentative association with it. But as Brad also pointed out there, they are in that gap of mini RF data. So there's no way to assess it in that way, at least at this point. Then the freshest crater category would be number 6 here, which I'm going to show you more of. Next slide. So this is a crater that is located on the top right of the in the map on the right-hand side of the slide. This is the freshest crater that we identified in the entire area based on NAC assessment as well as WAC color, which usually shows you the surface maturity to a certain degree. Next slide. You can see it on NAC, but in white color. You can see a brightening around the crater, so there's still the detectable ejecta around it, and all these block detections that you see. And this is not even exhaustive, but there's no matter where you go, you see a lot of blocks around this crater. So, and based also on the crispness of its rim, we interpret this as the freshest crater in the entire area. That is based on the white color and NAC data sets. Next slide, please. Now, the other things that should go into a map that can be used as a field map is certain features that you encounter on the ground, but that are very difficult to see in different lighting conditions. Therefore, they might be potential hazards. For example, the furrows on slopes, and also the blocks, which are themselves science targets. So I chose to look more at morphologic maps of areas that I've been to, for example, here in the Arctic and Spitsbergen and Svalbard, and get some inspiration from these kind of maps. So this is a to-scale comparison of both areas, just to get you a feel for it. Next slide, please. This is one of those blocky knobs. There are several of those, and they occur around Shackleton, and there might be degraded, fractured Shackleton ejecta blocks. So we could get information about disintegration, regolith formation rates on these. Next slide. And would be therefore very important to reach them. This needs to be in uncertain lighting conditions. For example, in this case, a certain azimuth 140 degrees west of elimination angle. Next slide. This is the aforementioned smooth crater floor. It's the only distinct geologic contact we see. And it's also part of a PSR.
Can you go to your last slide, Hans?
Yep.
We're out of time.
And that's also very challenging lighting conditions. Leave it with this slide. Oh, you could have left it with the other one. So elephant high terrain is the ubiquitous one, regolith textures based on slope. Thank you.